I'm going to take you through this problem involving an overbooked airline. I've created a Desmos calculator that you can use for it. I'm just going to show you how to use it so you'll be able to use it for other problems and not have to start from scratch. First, let me take you through how I set it up. I have some labels here for what everything means. We have to decide what n is going to be, and n and x are always related. So in this situation, we have a certain number of seats on the plane. That's not going to be our n, because basically they're going to overbook that flight. And so we're going to have really a certain number of people could show up that's bigger than s. Imagine a smaller scale example where it's 100 seats. They might sell up to 110 tickets. So the number of tickets is really going to be the upper bound for our variable x. That is always going to be the m. So think about n is really the maximum value of x. If x is the number of people that show up, then we could have up to as many tickets are sold. So there's our n and our x. S in this case, I'm letting that represent the number of seats. That really is not used in the initial setup. It's used more to determine the outcomes. So if S people show up, it's a full plane. If less than or fewer than S people show up, then there's empty seats. If more than S people show up, then there's too many people, or you could say not enough seats for the people that showed up. So I've really arranged everything around S. S is kind of going to be a boundary for values of x that we want to look at. So the other thing that I've done, I've put some boundaries on these. S, I'm deciding my plane will be from 0 to 300 seats. Has to be a whole number. P has to be between 0 and 1, and I decided to let that change by the hundredth. N is the number of tickets sold. They will not sell fewer tickets than they have seats. That wouldn't make any sense. If you had a 100-seat plane, why would you sell 50 tickets? You're going to start with 100 and then decide if you want to overbook it or not. So they're starting with the number of seats and potentially going up from there. You can't sell half a ticket, so that's a whole number too. And then for this last part, I will just redo that. You go to Keypad, Functions, go down to Distributions, find Binomial Dist, click on that. The inputs for that are n, p, and then set it up as cumulative. I'm going to make this into just black for the color. And then you'll have to, if you're making it from scratch, you'll have to kind of pick an x-axis that makes sense. About 240 to 280 is good for mine, or a little left and right from there. And then for the y-axis, a little tiny bit negative 0.05 up to about 0.15 is kind of where I started. If you zoom way out, you'll notice it's basically a horizontal line. If you kind of just start with your home arrangement, it really doesn't make any sense. So I really like to kind of bring that to the middle to really get a good look at it. Now you can make some adjustments if you want. You can slide some things around and see how everything is affected. We see that if they really sell exactly 280 tickets, that's a little bit lower here. If they overbook it, we can see that moving up. But we're going to start with just 94% chance, 280 seats, 280 tickets. And let's just start with a perfectly full plane. So that's cumulative probability of P of S, basically anything from S to S, just going to be one outcome there. That's approximately 0. In that situation, we have a 94% chance of each person showing up times itself 280 times. So every passenger gets that 94% chance. If they all are going to show up, that's basically a 0 probability. With this setup, if we wanted to find the probability of empty seats, we'd go from 0 to s minus 1. So you can see every outcome is highlighted except the full plane. There's a high likelihood of empty seats. The most likely outcome is 264 people arriving. So that's going to be 16 empty seats at about a 10% rate. The next question here says, what if they sell 295 tickets? So our N is moving up to 295. Now the probability of empty seats went down. So they overbooked it by 15. So sometimes they're going to overshoot that number. That's going to be over here. 280s right there. That would be a full plane. We're looking at empty seats. So there could be one empty seat, two empty seats. Most likely outcome is going to be two empty seats there. Again, around 10%. But the probability of any number of empty seats is 69.6%. The probability of a full plane is just looking at that one S outcome. That's 8.4%. And then if we go from S plus 1 and up, so you can leave max empty, or you could say 300, something like that, just beyond the capacity or beyond the number of tickets sold, that is a 22% chance. So this would be one too many people show up, then they have seats, two too many, three too many, adding all those up, it's about 22% chance there. So overselling by 15 tickets, it's still way more likely that they're going to have empty seats, which means they might oversell by 20 tickets or even more than that on a big plane like this. The next question is, how many tickets would they sell to minimize the number of empty seats, but keep the probability of not enough seats below 35%? So we want to kind of keep both sides at a minimum, but we have a specific minimum for the probability of not enough seats. So right now we're looking at not enough seats. If we go from 296 to 297, we go over that 35%. We want to keep that under 35%. Something you could do to make this problem a little easier is start adding additional distributions. So I'm going to make that one red for the overbooked. And the exact same function here with different ranges will give me the empty seat probability. So from 0 to S minus 1 is the empty seat probability. That's in purple. And why don't I do it one more time in black just for that full plane outcome. So now we can see the three outcomes side by side there. We want to keep both purple and red as small as possible. So keeping purple as small as possible is keeping the number of empty seats as low as possible. So if we focus on that only, we would want a high number of N. So the more we overbook the plane, the fewer empty seats there are. And right here I'm overbooking it by 20 passengers to get that purple region. Let me change this order. That will kind of make a little more sense here. So the purple region now is as small as I can make it within the bounds that I've set up. And I could take off this 300. Sometimes it doesn't work. Let's see. Yeah, it won't. Let me put it up to 400. Give myself more room there. So I can really overbook it a whole lot and get that probability of empty seats down a little lower. The problem is, there's another caveat. We don't want the probability of not enough seats to go over 35%. So here purple's pretty small, but red is too big. I need to dial it back. Now I'm down at about 48%. Next one down is 39%. Next one down, that's under 35%. So it's finding a balance between the two. Now purple is as small as it can be. The probability of empty seats is as low as I can make it without having the probability of not enough seats go over 35%. So the magic number there is 296 to balance that out. Is there any way that I can keep both of these, the red and the purple, below 40%? So right now, I've got one of them, the red, below 40%. If I move that to the right, it goes real close to 40%, one more to the right. So I can't even get to 40% on one without the other being over. It's just not going to be possible. The closest I can get to kind of a perfect balance between the two is overbooking by 18, selling 298 tickets. That's going to be about a 10% chance of a full flight, about a 43% chance of empty seats in purple, and about a 48% chance of not enough seats. That's going to be the area where it's kind of most in balance. Going a little bit to one side increases one and drops the other, and same with the other side.